Imagine looking up at the sky and realizing the mighty engine of our entire solar system has just frozen. Welcome to our latest explainer. Today, we're diving into a massive doomsday scenario. What happens if we halt the rotation of our local star? We're going to use this wild thought experiment to completely unpack how the sun actually works. Because, as you'll see, sometimes hitting the brakes on a massive cosmic engine is the best way to figure out exactly why it's so absolutely crucial to our survival in the first place. Let's get into it. So, here's the apocalyptic question right out of the gate. What would actually happen if the sun suddenly just stopped rotating on its axis? Would Earth instantly detach from its orbit? Are we talking about flying off into the freezing, empty void of space? Plunging into total darkness? It is a pretty terrifying mental image, for sure. But to really answer it, we first need to confront a super common misunderstanding about how gravity actually operates in our neck of the woods.
We need to quickly debunk a massive myth about gravity. According to the basic laws of physics, gravitational force is determined entirely by two things: mass and distance. Spin? Spin literally has absolutely nothing to do with it. I mean, unless you're dealing with extreme exotic physics, like the frame dragging around a supermassive black hole, rotation just doesn't generate gravitational pull, because our suddenly still sun wouldn't lose any of its actual mass. The planets, including Earth, would just keep right on orbiting, perfectly fine. No big deal, right?
Section 1. How the sun actually spins. The plasma engine.
Now, because the sun isn't a solid rock like Earth or Mars, its rotation isn't uniform. It doesn't just spin as one giant solid sphere. Instead, it operates a lot more like a brilliantly complex, turbulent plasma engine. This is due to a process called differential rotation. In astrophysics, this happens when a non-rigid object, so in this case, an enormous ball of superheated ionized gas or plasma, spins at different speeds depending on the latitude. Because of this plasma composition, the sun's equator moves at a totally different speed than its poles. It's essentially shearing itself constantly as it turns.
And these speed differences are drastic. The sun has an equatorial rotation speed of about 2 kilometers per second. That means the equator takes roughly 25 days to complete one full spin. But if you look up at the poles, they severely lag behind. It takes them over 34 days to make a single rotation. Imagine if Earth's equator spun significantly faster than the Arctic. Our planet would literally tear itself apart. But for the sun, this uneven spinning is just business as usual.
Section 2. The solar dynamo engine, creating the magnetic field.
This uneven spinning builds into something seriously dramatic. It acts as a colossal engine that generates the sun's most powerful, chaotic, and far-reaching force, its magnetic field. So here's how that solar dynamo actually works. Deep within the sun's convection zone, ionized matter is just churning away. This plasma is highly conductive, so it actually freezes the magnetic field lines right into itself. And because the equator is spinning so much faster than the poles, these magnetic field lines get carried faster around the middle. Over many, many rotations, they get stretched, pulled, and tightly wrapped around the sun, kind of like rubber bands. Eventually, these adjacent magnetic field lines become so incredibly packed together that they repel each other and violently burst right through the surface.
When those magnetic bands finally snap and burst through the photosphere, all sorts of chaotic things happen. First off, you get sunspots. These are the darker, cooler regions on the surface where the intense magnetic pressure has literally pushed the heat away. But worse than that, you get solar flares, which are just violent bursts of energy and radiation. And sometimes the whole shebang results in coronal mass ejections, or CMEs. These are giant magnetic bubbles of ionized gas that blast huge amounts of radiation deep into the solar system.
Section 3. A surprisingly safe solar system. The benefits of a still sun.
So, bringing it all back to our hypothetical, what if the sun just stopped spinning? Well, without that differential rotation, stretching and snapping those magnetic rubber bands, this massive magnetic dynamo would shut down completely. And ironically, a still sun would actually make Earth vastly safer from space weather. Without the dynamo, we'd see the elimination of massive solar storms. When extreme coronal mass ejections hit Earth's magnetosphere today, they can knock out global communications, damage satellites, and even trip entire electrical power grids. Without a spinning sun, that threat basically drops to zero.
And we actually have historical precedents for what a quiet sun looks like. Tracking sunspot activity over hundreds of years reveals a massive hiatus known as the Maunder minimum. This was a roughly 70-year period, beginning around 1645. During this time, the sun's magnetic field wasn't completely stopped, but it was remarkably sluggish, producing virtually zero sunspots.
There's a really striking duality to the sun's cycle here. On one hand, you have the stunning but potentially destructive beauty of active aurorae,
which are caused by solar disturbances slamming into our atmosphere. On the flip side, periods of really low magnetic activity, like the Maunder minimum and the Spurrier minimum, coincided with what climatologists call the Little Ice Age. We actually have historical records and paintings showing Dutch rivers freezing over completely solid. So, while a still sun removes the threat of solar flares, it might heavily disrupt our long-term climate.
There's another major downside to a still sun, too. The sun's magnetic field and solar wind act as this big protective bubble for the entire solar system. If the dynamo shuts down, that ambient solar wind weakens. This allows high-energy galactic cosmic rays from outside our solar system to just easily penetrate our atmosphere. By examining isotopes of beryllium preserved in polar ice cores, researchers found that during past solar minimums, cosmic ray fluxes spiked by at least 200%. This could impact cloud cover and pose severe radiation risk to air travelers and astronauts.
Section 4. The Galactic Freefall Twist, Stopping the Orbit.
Okay, it's time to introduce the massive twist to our thought experiment. Stopping the sun's axial spin isn't an immediate apocalypse, as we've seen, but what if stopping the sun meant stopping its orbit through the galaxy? You see, our sun isn't just sitting still in space. It is currently hurling through the cosmos at a staggering 500,000 miles per hour. It's on this massive 250 million-year orbit around the center of the Milky Way galaxy, which is anchored by the supermassive black hole known as Sagittarius A star.
If this galactic motion suddenly ceased, we would be in huge trouble. Without the forward momentum keeping us in orbit, the unimaginable gravity of the galactic center would just take over. We would begin a doomed freefall towards Sagittarius A star. Now, because it's 25,000 light-years away, it would take millions of years to actually get there, even accelerating at incredible speeds. But eventually, the entire solar system would be torn apart, literally spaghettified by the black hole.
However, we wouldn't live long enough to actually see that supermassive black hole. The immediate, sudden stop of the sun traveling at 500,000 miles per hour would unleash a catastrophic shockwave of momentum. It's highly likely this shock would catapult Earth and the other planets completely out of the solar system. We'd be violently ejected from the habitable zone, turning Earth into a rogue planet, frozen, permanently dark, and drifting totally alone in the interstellar void.
But, because we're determined to find the silver lining in this explainer, there is a bizarre one here. As we fall toward the center of the galaxy, the night sky would become a spectacular, constantly shifting canvas. Astronomers would have a front-row seat as we passed by entirely new star systems, alien planets, and strange black holes. But to actually survive this, humanity would be forced into the ultimate push for survival. We'd have to abandon Earth and build massive interstellar generation ships to hop onto a passing, habitable world.
So, we've survived our thought experiment. We've learned that the sun's spin powers a fascinating magnetic dynamo and that our momentum through the galaxy is literally the only thing keeping us from plunging into a supermassive black hole. It really makes you appreciate the delicate, moving balance of our universe. I want to leave you with a final thought today. If you were forced to board one of those generation ships with a one-way ticket into the deep Milky Way, what cosmic mystery would you want to unravel next? Let us know, because that might just be the topic of our next explainer. Keep wondering, and I'll see you next time.